Yeah, so welcome back, everyone. It's good to see a number of names familiar from yesterday, and I think I see at least one new name. As David has said, the recordings, the material from yesterday is available, but I'll start off probably with a very, very quick recap, and maybe that will help set the context. So yes, this is a two-day workshop introducing you to the tools that my colleague and I have been developing at ULIX Supercomputing Center, so Scalasca, Scorpii, and Cube, as installed and available on the ARCHER2 system. Yesterday we dealt with the instrumentation and profiling side of things, so getting an initial measurement that we could take a look at and then do some scoring and refinement of that measurement by applying a measurement filter, telling us specifying the parts that we want to keep in that basic measurement. That was what we started off with, and then there was time in the afternoon for people to work on their own codes and their own applications, either to work through the provided example exercise if you weren't able to follow that as we went through it quite rapidly. But the more interesting part was at least a few people showed me that they were able to apply the tools to their own codes, and we were able to take a quick look at them. We didn't look at them in great detail, but they were at least getting some measurements that we could start working with. So I would suggest that, can I quickly ask, was there anyone yesterday who had a problem that was not something that they could solve or we could solve with them? Is there something that we need to try and arrange to follow up with you based on doing the exercises with the tools or with working with your own code yesterday? Use raise your hand, please, if there's something that needs to be followed up on you from yesterday. I'm not seeing anything, so I think I'll take that as everything is fine. And as I said, we'll have an opportunity to follow up later today. Building on what we did yesterday, today's part of the workshop is going to be focused on trace collection and trace analysis using the instrumented executable that you built yesterday, and then doing some additional analysis of those traces with the Scholaska trace tools. And then there's lots more things that we can tell you about Scorpii and how to augment your measurements, how to customize the measurements in various ways. And that'll be something that we'll follow on to in the later part of this morning. And we have a few examples that we can also take you through of case studies that we have worked with that might be interesting to look at and discuss in more detail. Because the exercise we're working with is just a simple benchmark code. It's not of itself particularly interesting, but chosen for convenience more than great insight that you get from analyzing its performance. Okay, so now I'm going to switch over, which is always a complicated business here. So let me get out of those slides, and yes, I'll go into the Scholaska slides. The Scholaska trace tools are built around tools for automatic trace analysis, but there's a little bit more to them than that, as we'll see. The idea of the automated trace analysis is that it's possible by enabling tracing to collect a very large amount of low-level event trace data. Every event that your application executes, whether it's a message passing operation, some sort of thread operation, thread synchronization, or something else going on like entering and leaving a function, if we are collecting all those events, then we end up with a very large amount of low-level event trace data. This can run to many gigabytes, terabytes, even petabytes. And typically that's not so, I mean, that has complete information in it. You can certainly do lots of interesting analysis of that in various ways. But what we propose to introduce is an automated trace analysis, which is able to go through that very large amount of low-level data apply an analysis to it, and end up with something that's more insightful, that's high level, easier to work with. At the end of the day, we'll end up with a set of metrics that are calculated to augment the ones which are available in a basic measurement, where we're able to break down the execution times, not only into MPI time, but also into things like waiting time in various MPI operations, or waiting times at thread synchronizations. And those are the more interesting metrics that indicate where there are inefficiencies, where there are opportunities to improve the application performance. The trace analysis also would allow us to identify key characteristics of your application execution, such as the critical path, or the causes of delays on the critical path that are the things that are the most productive to focus on and try and reduce. And then from reducing your critical path, reducing the delays on the critical path, you're able to get a much better, or you're able to get a better time to solution, a better application performance. The automated, of course, you can do all that by looking at the traces and doing the analysis yourself. But the automated trace analysis has the advantage that it is guaranteed to cover the entire event trace. It's not going to miss anything. And because the way in which Scholastica has set up this analysis as a parallel replay of the events in the event trace, it's guaranteed to, or we can exploit the parallel computers that were used for the trace collection to make sure that the trace analysis can also take place in parallel in a scalable fashion. So whereas doing all of that analysis in a serial fashion might take a long time, or it might not be possible if it needs to load terabytes of data into memory. By exploiting the available memory and the distributed processors that are in the parallel computers that were used for the measurement, we can get the automated analysis in what's typically a fraction of the time of the initial measurement itself. And because it's also set up to run as an extension to the trace collection, it happens behind the scenes within the same batch job, so you don't have to worry about setting things up separately for that trace analysis. So those were that was an overview of the Scalasca trace tools. As I said, they were set up to provide a scalable form of trace-based performance analysis, supporting the most popular parallel programming paradigms. So MPI, obviously, MPI, and there's some limited support for other threading as well. The trace analysis that we provide that doesn't look into what's happening on GPUs or some of the other things that may be incorporated into the trace, but the things where there are delays, the things where there are parallel inefficiencies are in the MPI and Openmp, and that's where the trace analysis is focused. And then you can, of course, combine that with information that you get in the profiles that we saw yesterday, which are able to give you much richer information about what's happening on the CPU and at the GPU level. Our tools have been developed over a number of years. We've used them on the Blue Gene systems that we used to have around in Jülich, with millions of threads running on hundreds of thousands of cores. But there are also things that can work at smaller and medium scale as well. So Archer is a kind of interesting system as well. It's highly parallel. It has many nodes, many processes, and able to run many processes and threads, and therefore you can benefit from Scholaska in that environment, as well as perhaps on smaller clusters that you also use in your development. We'll be using the latest release of Scholaska, which is now a little bit old, but it has the functionality that we need. It's available as open source, like the ScoreP that we saw yesterday, like Cube, which we saw yesterday. It's, as I said, it's portable. It's been run on a wide range of systems, a range of the Cray systems, as well as the current Cray systems, which come from HPE. So that's a typo at the beginning of the slide there, HPE Cray, as well as a bunch of other systems with different processors, whether those are Intel processors, AMD processors, Power, ARM, etc. It works in conjunction with ScoreP, so we're using the capabilities of SCORE-P for instrumentation and measurement and collecting the trace, and then the Scholaska trace analysis comes in to do an augmented analysis. And we also have some additional tools that will process the basic reports provided by SCORE-P and by the trace analysis into a richer form where there's a more comprehensive hierarchy of metrics, and everything is, we believe, presented in a more structured form than just a serial list of metrics. There are a number of limitations which may or may not be important for the case studies that you're interested in. One of the key ones is that the threading model that is used shouldn't use MPI for multiple threads within a process. So threads on different processes are not a problem, but if you're using the serialized mode of MPI thread or the MPI thread multiple, when you can have concurrent thread operations, so the SCORE-P measurement system isn't thread safe for doing the measurements, and the trace analysis also isn't able to work out which events apply to which threads. So those are limitations that hopefully don't restrict the use for most of you, but they need to be borne in mind. And as I said, a lot of things like the hardware counter metrics, our usage information, those aren't things that you benefit from typically putting into the trace. It just makes the trace larger. So having the aggregated form in the profiles is typically sufficient. And if you're interested, we can also show you how to merge the profiles and traces together and see the hardware information, the hardware counter information from the profile combined with the delay analysis from the thread analysis, the trace analysis. So you get everything in a single presentation. So this is a different picture of the workflow, part of which you've seen yesterday. We went through the process of instrumenting the sources. Specifically, we needed to relink the source, relink the object files so that we were incorporating our measurement libraries. That resulted in a measurement executable, an instrumented executable that we could use for SCORE-P measurement. When that instrumented executable runs, we get our measurement libraries and other libraries linked into the application process, along with any libraries it itself uses. And then when it is running, we are collecting, in the initial case, the profiling case, we are collecting all of those measurements, aggregating them together in buffers per process, per thread, inside each process. And then at the end of the execution, we would write everything together into a single report file. This was the profile cubex file that we were looking at yesterday. We did a little bit of report manipulation, but in principle, you can look at the basic report, or you can do some post-processing of it. One of the things that we looked at was doing some scoring of it to identify the parts that are most interesting, most valuable, and we could use that scoring report to optimize the measurement configuration by deciding which parts we're going to filter out. And the filtered out parts we could then use, we could avoid the overhead of recording all of those filtered out parts in the measurement, making the report less cluttered in one sense, but also having less overhead and therefore more accurate. The main reason for doing the scoring was actually to also get the measurement configuration into a state where we could do the trace collection and trace analysis, which we're moving on to now. Because if we're collecting gigabytes of information per process, storing all that in memory per process is typically a challenge, or it's not possible. So it would be spilling out to disk, and spilling out the disk in an asynchronous fashion, an uncoordinated fashion from each process and thread, results in a severe amount of measurement intrusion and dilation, which we would really want to avoid. So we want to make sure that when we're collecting traces, we have a trace buffer that is adequately sized to store all of the information in memory, get us to the end of execution, to the MPI finalize, and then at that point we can write the event traces for each of our processes, each of our threads, and then we can analyze that. And what you'll see is that we'll launch the Scholastica trace analyzer. It also is a parallel application. It reads each event trace into its own memory, and then it will replay the events that it sees in that event trace. So where there are send and collective operations, send, receive, collective operations, it will be replaying all of those to construct and connect the information about what each process and thread is doing, so that it can then determine and provide its wait state analysis report. So that's an augmented set of metrics that are generated that can then provide a more comprehensive view of the performance and the performance issues in particular of the parallel application execution. It's in cube format, and so it has the same tools for interacting with it, including the GUI, which we saw yesterday, where we'll see how we can expand things like the time that we saw yesterday into not only the different parts which are MPI time or Openmp overheads, but the parts which are, for example, waiting at barriers in MPI operations or Openmp operations. And those are where time is being typically wasted. Okay, so that is the big picture. As I said, it's based, the trace analysis is based on replay. So where we have collected events for send and receive operations, as we're showing in the picture here, we know when the receive starts, we know when the send starts, but we know just by logic that the receive can't actually make any progress, or it can't complete until the corresponding send has been initiated. Depending on the size of the message, the receive would actually block until there's buffer space available and buffer space provided on for the receiver to here the receiver is blocking. It's providing a buffer for the data to be stored in, but the receive can't actually receive any data until the corresponding send has at least been initiated. When the transfer happens inside MPI, so that's a black box for us, but we know it can't possibly happen until the corresponding send is initiated. So that's the point that is indicated by the dotted line here. At that point, there's a potential for some data to be transferred, going into the buffer on the receive side, and then at some point the receive completes, the send completes, and we're on to the next operation. Something similar happens if it's a non-blocking operation where you have an iReceive providing a buffer. Again, there's nothing going into that buffer for it to be received until the corresponding send is initiated. That means that when there's a wait for that, what is it called on that handle? So the receive provides handles. The MPI wait will wait on that handle until the corresponding send is initiated, and then the send can complete and the message is transferred. The other cases with non-blocking iSends are in the same case as well. Until the send is actually initiated, until there's a chance for the data to be in transit, there's nothing that can be received on the receiver side. So that's for blocking as well as non-blocking communication. Another thing that comes from the trace analysis.
Brian, there's a couple of questions in the, sorry to butt in, there's a couple of questions that came in. You don't seem to be getting notifications of them, but in the chat, I did one, but there was a person.
How much does the type of hardware counters you can collect depend on the processor type? It depends completely on the processor type. And depending on what sort of events are provided by the hardware, and that's hardware dependent, you will be able to collect them. You'll be constrained by the number of events you can collect at any time, because some hardware allows you to only collect a few events. Other can allow you to collect many more at a time. The PAPI layer, this performance API layer that we use, provides some amount of insulation from that. So they provide aliases, or they provide presets that are standardized, so that things that are common, like the number of instructions, I think it's available pretty much from every processor. They provide a preset for that, so that you could use the same PAPI event on every platform and get something that corresponds to instructions. Whether those are instructions retired, instructions completed, instructions issued, might vary, but maybe you don't care about that level of detail. If you want things like floating point instructions, then you need a different counter, and that again would be hardware specific, and many processors provide that, many don't. Or to get something like floating point instructions, you may need to aggregate the measured events from lots of different counters. So for example, on Skylake processors, Intel Skylake, you'd have to aggregate what you get from single precision with double precision floating point operations, and there may be more you need to aggregate as well. Is it possible to get a similar visualization in Cube compared to slide 6? Cube itself would not provide such a visualization. There is a plugin that Cube, an experimental plugin that could provide such a visualization. I don't think it's installed and available on Archer, so we won't be able to show you that. But typically, the way we would look at event traces in these sorts of pictures are using a tool called Vampire. That's available on a number of platforms, but it's not available on Archer, so we're not planning to show you that either. I think those are the only two tools that I'm aware of that can present the sort of trace data that SCORP is able to collect. Of course, there's other tools from Barcelona and others that can present such pictures in from other trace formats, but typically we don't have converters between those. So that means that what you will see in the Cube presentation is the kind of profile that you were seeing yesterday. So a very abstract, aggregated presentation, where for each call path and each process and thread, you get an aggregated value, as opposed to seeing the individual events, which are what we're looking at in the pictures here. We can discuss, I think, some of those details a little bit later, perhaps. But the other thing that you get from such a picture is a perspective of the critical path. So the critical path is a determining path through the events on the different processes and threads that is governing your time to solution to time to completion. That is, in this case, relatively easy to see for 3 processes here, where we have the middle process is having to wait for data that is receiving from the one at the top, and the one at the top is having to wait for data that was waiting to receive from the process on the bottom of the lower one here in this list. So by working through that chain of events, we can identify what is the critical path and how much of the critical path is spent on the different processes and threads, and what they were doing before they reached the events that are the transfer events that change the critical path from one process to another. With 3 processes and a handful of events, that's perhaps something that is relatively manageable to do in a visual fashion. But if you're dealing with a typical trace with many millions of events, maybe many hundreds and thousands of processes, then the automated perspective of that is perhaps more appropriate. I'm hearing more beeps, but I don't see anything more in the chat, so I assume that there's nothing I need to worry about there. And then once we've figured out those transfers where one process is waiting on other processes, we can also work back and figure out is the reason that the process at the bottom is waiting here in a receive. It's waiting on the data from the middle process here, but that middle process was actually itself delayed waiting on what was happening, waiting on a message that it was waiting to get from the one at the top here. So some of the waiting time on the lower process here we can say is direct waiting time for a message transfer, and part of it is indirect based on a message transfer that the one it was immediately waiting on had to wait for. So we can work through these back through these chains of events to figure out what is the cause of the delay, what is the computation that was leading to all of this delay. So here it was the foo computation on the top process that took longer on that top process that caused this chain of delays. So if we were able to reduce this highlighted part of foo on the top process, we'd have things nicely balanced, and then the communication transfers that follow on from that wouldn't have the delays associated with them. So that would make them occur much faster, and then allow us to complete this chain of operations more quickly. So those are the sorts of things that come from the trace analysis that are they're possible to do in a profile fashion while the measurement is going on, but as soon as you start sending extra messages, you are interfering with what the application itself is doing. So those are something that's typically something we would want to minimize and reduce as much as possible. So that's why we store the events in the traces, and then we do a postmortem trace analysis. Writing and analyzing the traces is itself expensive, but it's worthwhile doing it in that form because it avoids the interference with the measurement that we're actually doing at the time, or interfering with the application at the time when we're doing the measurement itself. Okay, we'll come to hands-on in a little bit, but I'm going to be introducing you to Scholaska. Scholaska is the tool that, or the Scholaska command that allows you to do the different parts of things. We already saw how to do the Scorpio instrumentation yesterday, so there's no reason to use Scholaska for doing that. But we'll move on and look at the Scholaska analyze and Scholaska examine. Those are two the two key parts. So one part of it is taking control of the application execution so that we see and control how it executes, and then we can, after we've done our trace collection, we can do the trace analysis in the same configuration, and then the Scholaska examine will be our augmentation for looking at the analysis report. So someone yesterday was talking about square as a complement to cube. You'll see how square allows us to do that post-processing. It ties up the loose ends and provides the additional structure that we can then exploit when we're looking at things in the cube GUI. Shortcuts for Scholaska Analyze and Scholaska Examine are scan and square, so that saves a little bit of typing, and is a shortcut that at least we find convenient to use. So if you remember the names scan and square, or you hear the names scan and square, scan is the Scholaska Analyze, square is the Scholaska Examine. What scan is doing is, as I said, taking control of the measurement environment, setting additional environment variables, making sure that they're correctly exported to the different processes, which some batch systems do automatically, others don't. So scan can help with that if it's helping there. It will also automatically try and figure out an appropriate name for the measurement. So you were doing that explicitly, you can continue to do that explicitly, but by looking at the command line options of the batch execution, we can figure out what you're executing, how many processes and threads you're configured with, and encode that into a suitable experiment title, so that by just running, by using the scan alternative to running things without scan, you get a title for your experiment. The other thing is that scan will do some consistency checks, making sure that things are set appropriately, and at the end of the measurement, it will make sure that it has things in the right way set up for the trace analysis in particular before launching that trace analysis. So those are consistency checks that you might find you don't need, but they're there and they provide a little bit of extra security. For example, preventing the corruption of a measurement. If you do multiple measurements at the same time, you'll end up with them all messing each other up. They'll all be corrupt, and you'll probably end up with nothing that you can make any sense of. Scan will abort in that circumstance and say, you have an existing measurement here, move it or rename it, and reconfigure things in a way that avoids having to mess around and change an existing measurement, which maybe you're no longer interested in, but it's there and we don't know what you want done with it. Okay, so that was the scan, and the other options for Square for the trace analysis report processing is a bit more straightforward. We'll see that in a moment as well. So I think I'm going to switch at this point back to a terminal session and go through things live. Since I find it inconvenient to switch back and forward between the slides, you're welcome to follow the slides on your own if you prefer. But information is on the slide about the different steps that I'm going through, but I'm going to show you things in the terminal session, and that I hope is sufficient for you to follow. If there are things missing or you get out of sync, the slides will allow you to get back up to speed. So the first thing is, of course, we need to log back into to Archer and set up the environment again as we had it before, as we had it yesterday. So we're going to switch back to the GNU environment, load the other software so that we can get Scholaska. And we'll be working with the BTMZ exercise that we configured and set up yesterday. Just checking who do we have as still. I think we mostly have people from yesterday, but maybe there's maybe it's still useful to do a quick recap of what we did yesterday as well. So let me switch to my terminal session. Okay, so I'm logged into Archer here already. So all of the password stuff is gone. And I'm in the default environment, so I need to swap the modules around so I get into the GNU environment. I don't know if anyone used the Cray environment yesterday, and I didn't see any comments about it, but you're welcome to try it if you wish. But the GNU environment is what we recommend and is set up and working better. You see that the load EPCC module is already there, so I can load other software and Scholaska. And what's going on here? Of course, I have to load the other software and Scholaska, and now I hopefully have the module loaded and I have Scholaska on my path, as well as Cube and Scorpy and everything else that we were using yesterday. Okay, I'm in the work directory that I was using yesterday, so I already have things built here, but just to quickly remind you that if I do make suite here, it is building and compiling everything without Scorpy instrumentation, so that's a reference version that I could build and run. were job scripts provided for ARCHER2. There's also ones from Archer which are no longer relevant because it's no longer around, but in principle I could use those for reference if necessary. So that's an uninstrumented reference execution, but what's more interesting is doing make clean and building everything with the Scorpio instrumenter. So hopefully you remember that we're going to take all of these Fortran compiler commands and we're going to prepend or add a preposition here for the Scorpio instrumenter to those. I can go into the make file and do that. If I'm too lazy to mess around with the make file, I can just edit the line. So instead of Fortran, I'm going to do Scorpio and add any options I want to Scorpio, such as the user instrumentation. And now when I do the make, all of my Fortran compile commands have this preposition for the Scorpio instrumenter. This benchmark is set up so that it puts the new executable into a separate directory. That's just for a little bit of convenience here. Your build systems presumably won't do that, so you'll need to you'd be overwriting any previously installed and sorry, not installed, previously built executables. So here I have a measurement. I'm going to just run that as I did before for fun. So let's see what happens. But I'm also going to copy the Scholaska job script because that's going to be a little bit more interesting for us. And if I look at what's in that Scholaska job script, I will see how I have modified it. I didn't want to submit it, I wanted to copy it. Too many things at once. I think I've ended up with a bit of a mess here. So those are running. That's maybe even complete. Okay. So what you saw here was that when I just ran the instrumented version of the executable here, without doing anything at all, I'm getting a default measurement. That was this directory here. I'm going to delete the other one because it's in the way at the moment. So during the measurement itself, I ended up with a temporary directory, and then at the end of measurement, this was automatically renamed by Scorpio to give it a name based on the date and the time and some unique number here. If I had multiple measurements running at the same time, they would all be writing into this directory and corrupting it, and you'd end up just with a mess. But if you get to completion, then you get a default name for the measurement that at least is unique and allows you to see when it was run. And inside that, you will also have the Scorpio config information that tells you how it's configured. And all of that is just the default configuration information. So I didn't specify anything. You got a default measurement, default configuration. So now I'm going to look at this Scholaska batch script and see how to adjust that. Inside the batch script, I'm loading the Scholaska module so that I have access to the Scholaska analyse command or the scan version of it, which we don't actually want the -t in here, not initially. So if I run this, I'm going to I'm using the Scholastic analyse here as a prefix to our srun or MPI exec and our instrumented executable. One of the things it's going to do is it's going to check this executable for its instrumentation, and it's also going to figure out how to run it. And that's going to be based on what srun provides. It's going to figure out the number of threads in this case, which is 6, and the number of processes, which is further up here at the top. So tasks per node is the number of MPI processes, in this case 8. From that, it can work out what it thinks is a reasonable default name for a measurement without us needing to explicitly specify it. Explicitly specify it if I set score P experiment directory. But we'll just let Scholastica take control. We also saw that there's a benefit in using a filter file, and so I have the filter file specified here in the job script, and we'll go ahead and use that. These other options here are not relevant at the moment, so I'm just going to ignore those. But perhaps we're interested in having some hardware counters, so let me uncomment that. I'm not sure if PAPI FPOps is supported on the system here, so I'm going to comment out that. And so now I'm specifying that I would like to have 2 hardware counters included in my default measurement, which is going to be a profile. So let me, before I submit that, I'm going to make sure that I specify the reservation here. Today is Tuesday, so it's the second line here. So when you run things yourself, make sure that you uncomment the right line here. Otherwise, it'll go into the default queue. It'll run, but it will be taking resources that are best used by other people, because we have a reservation for the course here. Okay, so hopefully that will start and run relatively quickly. I have the output from the reference execution here that I can take a look at. It's a fully instrumented version, so as we saw that it's taking about 40 seconds here, which is quite a bit more overhead than the reference version, which is in this other directory. 4. So my reference execution here was only 11.5 seconds, 12 seconds. We have, in the default measurement without the filter, we have quite a lot of additional measurement overhead, which is why we're using the filter file. Rather than getting one of these score P names with a date and a timestamp for the directory name, I now have the version that the scan command came up with, the Scholastica command came up with. It took the name of the executable, in this case btmz_c. It took the execution configuration, the number of processes and threads per process, and it is telling me that it's a summary measurement, which is just what the default measurement configuration is. Inside that score P directory, I have a couple of extra files here. I have a profile that we could take a look at. We have a copy of the configuration, and I'll see inside that configuration that I have various things set. So the experiment directory has been set based on what Scholastica came up with. I have the filtering file being specified, and I have the hardware counters being specified. So the things that I specified are in there, augmenting what is the default measurement configuration here. The other file that we haven't seen before is the score P log file. So again, what Scholastica did was it just captured the output from the application execution and stored it in the log file here. So I don't have to look in the job output itself for this. It's saved in the experiment directory, There's a little bit of verbose information here at the top, just confirming when it was run and how it was run. At the bottom, it will confirm how long the measurement took, 14 seconds. And we also see that the time in seconds for this measurement is now down to 12 seconds. That's because we were using the filter file. So it's important to use the filter file. It's important to check that the filter file is appropriate for the measurement that you're doing. So let me, that was the default measurement, and I could look at the profile with Cube. So that would be Cube running on this directory, on this profile. I'm going to skip that because I'm going to instead use Square. And Square can work with a Cube file if you give it one, but it's more interesting to use it with the directory itself. And what it's going to do first is it's going to do some post-processing of what it finds in that directory. It found the profile, and it's now reworked that and produced a summary.cubex stored in that same directory. If I compare the size of those two Cube files, I'll see that the post-processed version is larger. It's quite a bit larger here, and it's larger because it contains the additional metrics, which I am going to be showing you in a moment. But for that, I need to again switch to a different window. So from this window, and so Cube has come up full screen for me, which is inconvenient because I have to share it with you. Here we go. Okay, so hopefully you're seeing my so this is my my measurement now. What we are seeing on middle and right-hand side should be very familiar to you. What you saw yesterday are 8 processes, each with 6 threads. In the middle, we have the application executable with the different call paths of execution, including the part that we explicitly marked as being of interest here, which is the iterative solver. But what has changed is we no longer have just a simple time hierarchy on the left-hand side. We have structured that to be able to see the time for computation, the time which is in MPI. And when we look at the time in MPI, we see our MPI init, which is not very interesting. We see an MPI barrier, the MPI reduce. We also see where MPI is used inside the exchange QBC, exchanging the boundaries, and where most of the time is spent here. So by figuring out which call paths are MPI call paths, what the post-processing has done has determined that there's 9 seconds or 1.4% of the execution is MPI time, and we can click on that metric and then see where that time is spent, which processes and threads are spending that time. The same for Openmp. Here, the Openmp is mostly in the ADI, and then inside here we'll have our parallel regions for which are here, and then inside those, the Openmp parallel do, etc. So this isn't the time inside the Openmp parallel region itself, the computation time. That is actually what we would consider useful computation. So that's part of the computation time metric. What is shown here are the Openmp overheads. So the overheads for synchronization or other things that Openmp might be doing, barrier synchronization or critical sections. So the Openmp barrier synchronization is either explicitly, there's no explicit synchronization in this case, but it's all implicit barrier synchronization at the end of the different parallel regions. So each of these parallel regions has an implicit barrier at the end of it. It's also telling me that there's a critical section. It's a negligible amount of time, but I can also find that easily by selecting it. It's telling me it's part of the verification code. So it's not part of the time and benchmark, so it's probably not something I worry about too much. But inside here, I'm seeing the atomic that is a critical section. Well, atomics and critical sections are aggregated together in critical time, critical synchronization time here, but we have those showing up for the corresponding threads which are executing that atomic. If I switch to the visits metric, we see that they're all executing that atomic the same number of times on each thread, but the time that they take, which is negligible, is something that might vary. Just as I could distinguish the, I distinguished the Openmp overheads. Everything that is MPI is considered overhead. In principle, you may have something like an MPI user-defined reduction or something, which could be considered computation, but those are typically very small, and I think we still consider those to be part of the reduction itself. So things like the collective operations here are where reductions would take place. We have a reduction down here. Negligible amount of time in the reduction. Most of the communication time is, in this case, point-to-point time, where we are seeing the time in the sends and receives. It's not showing the wait all as point-to-point time because the wait all is a multi-purpose operation that can complete lots of different non-blocking operations. They may be non-blocking point-to-point operations, they may be non-blocking collectives, it may be non-blocking MPI file I/O. So that's why we actually consider that separately here. So it's not considered communication in this case. We're unable to split the time and the wait all in general into the parts which are point-to-point, collective, or file I/O. So at the moment, it's all aggregated together and shown as part of the request handling. And specifically the request completion here. So the way in which things are structured here might take a little bit of time to familiarize with, but it provides a little bit more structure for exploring where different types of operations are. Here we have the collective synchronization, which is a barrier in this case. MPI management operations, things like init and finalize, or where there's operations based on communicators. So things like com split, com rank, or communicator operations. There's no MPI file I/O, but that would be another category inside MPI. Categories which are not relevant are going to show up with 0 time for them. There's another metric here which I think is worth mentioning for Openmp applications or hybrid applications. Here we're derived an additional metric called idle threads. Hopefully I can get some documentation for this. Nope, it's not found the documentation for it, or at least it's not showing the documentation for it. Yeah, too bad. What idle threads are, maybe I'll maybe you'll find it later. Idle threads are an additional metric we have introduced to allow us to keep track of what's happening outside of the parallel regions. So we know our MPI is outside of the parallel regions. All of the MPI activity is happening on the master threads. When we're inside the Openmp parallel regions, we have various activities on the Openmp threads as well. But outside of the parallel regions, those threads are going to be not doing anything useful. So that's why they're going to be showing up as idle time here. So the idle time here won't show up on the master thread typically. It's typically for the additional threads that are in the Openmp teams that are not actually being used at that point. So if I find where there's some computation going on, this is all very small amounts of computation. Sorry, here's the computation. So we have different amounts of computation on each of the threads here. We have the barrier synchronization at the end of the execution. If I select the computation and the synchronization together, I see that within the parallel region, all of that time is accounted for. It's all accounted for as computation or as implicit barrier synchronization. But if I'm outside of the parallel region, and if I go now here, I see that that's no longer the case. Here, there's some additional computation that is outside of the parallel region, and it's only executed by the master thread. And that means that those other threads are going to be idle for that amount of time. So here, this 0.02 seconds on rank 0, but can be different amounts on the other threads, is going to be attributed as idle time. So this is our way of accounting for the fact that those CPUs are allocated to the job. They have initiated some threading computation here, but they're not being used outside of the parallel region, and therefore that is idle time that is being wasted here. We also saw the bytes transferred yesterday, which we can break out into the different parts which are sent in the send operations, received in the MPI wait alls, and also the data sent incoming and outgoing in the collective operations. So for something like a reduce, we have all of the data being received by one rank, but all of the ranks participate in sending data to that root of the receive operation. We also have the additional hardware counters that I added in here. In this case, cycles is going to show me more or less the same as computation. The instructions are the number of instructions that are executed. If I was interested in that, I could see that as an additional metric for each of the call paths and how it might vary across the different threads.
Brian, there are two questions in the chat, so last two ones.
Square is an alias for Scholastica examine, but the name Square is confusing as it's more powerful than cube. So Square is a complement to cube. It is augmenting what you get by looking at things in cube. So I can still look at the initial profile here in cube. Where is it? Open the profile. So this is what the basic score P measurement had, and just had time here. It has the hardware counters, it has bytes sent and received, but it doesn't have the hierarchy. That was something that the Scalasca examine, the Square produced. So you can think of thing as being more powerful. It's doing the additional post-processing that helps you get more information out of cube. It's a complement to Cube. If you don't find the additional information useful, you can still look at the basic information in Cube. Someone was asking about finding 3 dimensions too much, that they wanted to reduce things to 2 dimensions. Of course, you can do that in Cube as well. If I just want 2 dimensions, I can see 2 dimensions here. If I find 2 dimensions too confusing, I can go down to a single dimension, and then I'm just dealing with a 1-dimensional profile. So if you find that too much information is confusing, you can get rid of it. If you find more information is helpful and can work your way through it, the structure that Square and the additional analysis that it provides is one way of doing that. So if you're not seeing the breakdown, then you didn't run Square, and therefore you didn't, as I said, in Square, you can look at the profile directly, but if you just run Square on the directory, it would automatically find the most appropriate, the most comprehensive report and show that automatically. So after doing the post-processing to produce the summary.cube file, that was the one that it produced, that opened up and presented. I'm going to exit from this and go back to the command line. How are we doing for time? It's probably a reasonable time to take a break if people think that's necessary while I'm switching back to the other slides, or because we've mostly been focused on a recap up until now. One of the things that I didn't show you that I can quickly show you is that Square I can also use as a convenience to do the scoring. So by giving it, again, the directory name, Square-S is the option to say do the scoring and store the score report in the archive directory here. So I can run score manually. This is the command that Square ran for me. So Square-S is the command that would allow us to automate that. I have the same score P report as before, showing me what I need to see in here. There are different options I can use to the Scholaska examine, or just the scan command, which just running it on its own will, the Square command on its own would give me the basic options. Square-S was for scoring. I can give it a filter file and have that applied when scoring. Various other complicated stuff, which I don't think I need to explain here. So as I said, I think I'll take a break for 10 minutes, and we'll continue at quarter to the hour. If there's any more questions, feel free to put them in the chat or ask them verbally. Let me, and we already covered things quite a lot on the slides, but I think I'll start with the slides for the next part, and then hopefully avoid too much switching back and forward. Where are my slides here? Okay, so we saw how the Scholaska scan command can be incorporated into the job script when you're doing the measurement, and can give you a little bit of extra support for how the measurement is done and what you see when you do the post-processing with the Scholaska examine command. So that's more or less what you could also do on your own yesterday. So you haven't really seen anything new, but maybe you've had some seen some benefit from doing things in a slightly different way. We're now going to move on to do the trace collection and analysis, and this is the new part, but it builds on how we're seeing Scholaska being used for the profile and summary collection. We're going to be using the scan command, the Scalaska analyze command, and we're going to add this -t option to it. That's the tracing variant. The default was for S, which was for summarization. By doing the -t, we're going to switch over into this new mode and do the trace collection. For the trace collection, we want to make sure that we're using the filter file, which we already did, and we want to make sure that we have an adequate amount of score P total memory, so that we can have the traces collected in memory without worrying about them being flushed to disk. In this case, it wouldn't be the end of the world. We wouldn't get people screaming at us on Archer about filling up the disk. But for your applications, I think someone yesterday showed me an application that would generate a few terabytes of data. They'd probably have people screaming at them very quickly. We'll see that when we run this under the scan control, it's going to say it's configured a new type of collection and analysis. It's giving it a trace suffix to the experiment directory name. So we're not going to, we're going to be storing the results in a separate directory, separate from the summary that we already have. And at the end, we'll see that it automatically starts the trace analyzer. The trace analyzer that Scholaska uses is called Scout. There's different versions of it for MPI or for hybrid applications or pure OpenMP. If we were running on multiple nodes, we would also give it some more additional arguments. Time correct allows it to do the time correction to synchronize clocks from different nodes. Since we're running on a single node, it's redundant, but it doesn't hurt to include it. And in this case, we're also seeing some output from the trace analyzer as it runs, producing the new trace analysis report, which we would then be able to look at as before with Square. Square would do the post-processing of the scout.cubex file and produce a trace.cubex, and then present that to us in the analysis report GUI. And then we'll see the additional metrics that come from that. So how does it look in practice? Switch back to the terminal session. Stop that one. Share. Okay, I am back in the terminal session in this directory. We looked at the scoring output, and from the scoring output, it was telling us what were the memory requirements. In this case, 95 megabytes for score P total memory to avoid intermediate trace flushing. So that's what we would need to put into our job script to make sure that we have an adequate amount of memory to store in the trace. Of course, the version that I have already includes that. Here it's rounded up to 100 megabytes. It doesn't hurt to have a little bit of extra, but the 95 was an estimate. I wouldn't recommend going lower than what is estimated. In principle, there is some compression that's applied in memory to events, so the 95 should be conservative. It should be guaranteeing you that everything fits in memory, but when we have 100 megabytes available, and we certainly have 100 megabytes per process available here, then we're certainly able to provide it. This memory is per process, so all of the threads are going to be writing into buffers on the same process, and that 100 megabytes is for all of the threads for each process in total. Each of the processes has their own 100 megabytes, but each of the 6 threads of each process will be sharing that 100 megabytes. I'm going to comment out the hardware counters because, as I said, there's no real value from including those in the trace. It's just additional overhead, additional detail that the trace analyzer isn't going to look at. We could specify a measurement directory, but I'm going to leave scan to do that itself. We need to make sure we have our filtering file here, and I'm going to leave the scan analyze options here. Time correction is primarily for multi-node execution. And then I can modify the scan command here to add the -t flag. If I prefer, I can do it more explicitly with score P here. Score P enabled tracing is also telling Scholaska that I want to do trace collection and trace analysis. So I don't need both, but it doesn't hurt to have both here. The -t option on its own is generally more convenient, but if you prefer to set the environment variable, set the environment variable instead. So now I'm just going to go ahead and resubmit that. You can resubmit yours if you've made those modifications. What I should hopefully see is that it starts relatively quickly. Something, yeah. So it's created a directory, but the directory probably won't contain very much at the beginning. It's created a copy of the configuration and the filter file that it's using. It's created a directory for traces, but that directory has empty files in it at the moment. So the files are open, they're ready to be written, but they don't actually contain very much at the moment. Or maybe they already do, but in principle, all of the files are open as part of the initialization, so there's no additional overhead from opening them and writing to them in the course of measurement if that turns out to be necessary. If I look in the job output itself, I will see what I was suggesting we would see, that this is the command that I'm running. It's telling me that I'm doing trace collection and analysis. First stage is to define a trace experiment archive directory, which is going to use. Going to run the executable. It ran in 12 seconds, so there's no real overhead added from the trace collection here. Trace collection finished in 14 seconds, and then it automatically proceeded to move on to the trace analysis. Trace analysis is launching our trace analyzer, which is an MPI application. So it's launched with MPI run. It's hybrid, so it can handle the threads. This is the time correct argument that we provided to it. And then it's working on the traces in that directory that was just generated. The trace analysis itself took 10 seconds, so it was a little bit faster than the trace collection. And it's telling me at the end that it generated 128 megabytes of data. That data is still there. It hasn't deleted that. You might find some value in keeping that trace data around. Now that the analysis is complete, in principle, the trace data could actually be deleted, but you never know. Until you've looked at the analysis, you may actually want to repeat the analysis. You may have forgotten the time correction, for example, so you might want to reanalyze the trace, adding that. Or, I don't know, maybe you have some other reason that you might want to keep the 128 megabytes of trace data lying around. So what's in the directory now?
Brian,
Yeah.
Can you show the changes to the job script again that you made for the tracing run, please?
The only important change was to either define this environment variable, which is here commented out, or add the -t. Verify that you have the filter set, which the script already has. Doesn't really matter whether you include hardware counters or not. And here we are specifying an adequate amount of memory, which was already specified there, so you shouldn't need to modify it. So for the provided job script, I mean, assuming that you already set the reservation, which are the two parts up here, the only important change was to add the -t. And when it runs, you should see something like a trace directory, and that trace directory would then contain all of the different artifacts that are produced. So we didn't disable the profiling, so we still have a profile. That's where the hardware counters would go if we still included that. We have some additional files. We have the traces directory, which has the trace data, which, as I said, could be deleted. We have some additional statistics from the trace analysis, but the main thing was that we got a log file from the trace analysis from Scout. That's just for checking how things are running or seeing if there's any error messages from Scout. It's just a record that it ran, how long it took to run. But then the most interesting part are the different cube files that was produced, including the new one that was produced by Scout. This was the initial the profile that was produced. This was the trace analysis file, which has some additional metrics, and that's why it's a little bit larger. When I switch over to Cube, I can show you the format of it, but it's just a flat list of metrics that doesn't have any important structure to it. So really what I'm wanting to do again is to run Square on this new directory, and that new directory will be processed. It'll process all of the different files that it finds in there. So it processes the cube file from the Scopy profile, as well as processing the scout.cube file into a trace.cube file. And then it brings up cube, which I have to catch and bring into collaborate. Let me try again. Okay, now Cube is open, and now I can share it. Okay, now I can share it. Okay, so now what we're looking at is the trace.cube file. That's the one that the Square command generated and thinks is the most relevant one to look at. It has the most information. At first glance, it'll again look very similar. What we're looking at in the right-hand side hasn't changed. We're still running on a single node. We still have the same call path. That's not going to change. We still have time, we have visits, but we have a few other metrics that are now appearing here that we might want to take a look at. The one I'm going to look at first is the time hierarchy, because that has been augmented. And at the highest levels, it looks the same, but we have MPI time, we have Openmp overheads here. The reason that there's a highlight around these is it's to indicate that there's more information down below it that could be coming from the trace analysis that could be interesting. So here, it's not just telling me the time in the implicit barrier, but how much of that time is waiting time. How much time is in the collective communication, but how much time of that is what it's calling early reduce, where we're in a reduce operation that has been initiated on some ranks before others. Probably the help information would work now, yeah. So early reduce, the diagram here is not a picture of what actually happened, it's just a diagram explaining it. We have three processes, multiple processes doing the reduction. Two of them One of them is the root of reduction, where the results are going to go, and it cannot complete until all of the others take part in the reduction. So that's why it is blocking until this point, when it has the data from the last of the others have arrived, and then the reduction on the root can proceed. So in this case, the early part of the reduce, the part that has waiting time, is only on process 1 here until the last rank entered the reduce. That is waiting time on the root node of it. For for other point-to-point operations, we already saw those diagrams where the receiver is blocking and having to wait for the corresponding send to be initiated. For the barrier, here it's telling us that we have multiple processes. All of the processes have to wait until the last one reaches the barrier. As soon as the last one reaches it, in principle, the others are able to proceed. Until that point, they have to wait. So the red lines here are the waiting time that would be shown for those corresponding processes waiting for the last one to reach the barrier. Here we're seeing the waiting time, which is negligible for each of those. The late sender time, which is relatively small. The wait in the reduction is negligible. So this benchmark is not showing large amounts of waiting time. You could execute it in different configurations, and we'd see more waiting time in the MPI. Actually, most of the waiting time is at the Openmp level, where you have imbalance within the parallel regions. That load imbalance in the parallel regions results in extra waiting time for some of the threads. It actually turns out that it's the higher ranked, the higher numbered threads that have more waiting time. That indicates they have less work. So most of the work, or the excess work, has been allocated to the lower ranks here. And if we were to look at that in the topological presentation, perhaps you can see that here we're looking at an array of processes and threads. So each thread is represented here as a block, and each column of threads represents a process. The higher values are the darker blue here, but they're all very small because there's 48 of them, so they're all very low values. If I switch to the peer percent mode here, interesting. What you're seeing is where the mouse is pointing to doesn't correspond to what I'm seeing, but I'm selecting peer percent here. And peer percent is showing the variation of waiting time. The ones on the master thread have the lowest values here. The ones on the second thread have a little bit higher values, but it's still very low. And most of the waiting time is actually on the highest rank here, which has the darkest red and orange color. So that's an indication of the load imbalance within the iteration itself. And we'll see that variation differs for each of the solve directions. For the X and Y solve, it's a very pronounced imbalance where there's extra work on the first two threads and the others are pretty much the same. Whereas for the Z solve, it's a little bit more of a mixed up picture. There's still the same pattern of imbalance, but it's more, there's more variation and it's more progressive as opposed to being very pronounced here between two threads on each process and the others. What else do I want to show here? Critical path. As I said, we can calculate the critical path. Here it's telling us that there's 13 seconds of execution on the critical path. This isn't from the beginning of main to the end of main, but it's from the MPI init to the MPI finalize. So only the part that's MPI parallelized is considered on the critical path. What we're seeing in the topology isn't particularly helpful, seeing that some of the critical path is on two of the processes but not on others. It's more relevant to focus on the critical path in terms of which parts of the code are on the critical path. For this application, they're all executing the same code, so they all have the same contributions to the critical path. But for other applications, you might see a difference in terms of what's happening on the master processes, or what's happening if you have a task farming. Maybe the task farmer has a different operation, different contribution to the critical path to the other ranks. Imbalance on the critical path is what we might potentially gain by magically being able to balance things and avoid load balance. And again, it's showing us where we had imbalance in the parallel do loops of the different X, Y, and Z solve. That's where most of it is imbalanced. There's also some imbalance in the exchange here, but it's a bit more spread out. I think that's probably enough for this. Someone was asking about if I didn't want to see the tree structured metrics, but if I went to the flat tree, then instead of seeing things like ADI multiple times, I just have a single entry for ADI. In the call tree, that appears in different places. But if I want all of those aggregated together so they just appear once, then the flat tree representation is what I want to look at for that. The same is true for things like MPI reduce. If I just want to see all of the MPI reduce times for the whole application, I would have to find it. It's not a large amount of time here. So this flat tree representation, typically you need to sort it. So sorting things by name is one way of sorting things. Then I can find things a little bit more easily. But I can also sort things by the metric values as well. So if I sort things by the exclusive value, then in principle, it should tell me where the different parts are spending time. Subroutines here is telling me that within, that's, what is this 8 corresponding to? I guess it's the name of the executable or something that's not very meaningful here. Probably it's simpler to start by sorting things by the inclusive time. Okay, so the things sorted by inclusive time are where the majority of the time is spent, and I can work down through that list to see that a large part of the time is in ZSolve, but it's not in ZSolve itself, but it's actually in the subroutines, in this case, the parallel regions, which are called from ZSolve, which conveniently enough are actually shown here, but they may actually be lower down in this list. If I wanted to see the things sorted by exclusive time, I think the best way is to expand everything and then sort by exclusive time.
Brian, we don't see the pop-up window if you right-click and select then expand, collapse all, or sort tree items. So we don't actually see how you do the sorting and the
that's
expanding.
nice.
So you just need to right-click, and then an additional menu comes up, and you can select different options there.
Yeah, and I can't show you this because Collaborate is choosing not to share that information with you. But yeah, you don't see the menu or the additional dialogues. That's a bit unfortunate.
What's happening, Brian? Sorry, is it because you're sharing a window, not a screen? Is that why? Is it treating the new menu as a different window?
Yes. When I'm sharing a window, it is not sharing all of the dialogues and things that come from that window.
It thinks they're separate windows. Okay, I understand. Fine.
Well, they're certainly not separate windows. The dialogues might be, but even the menu items, when I'm going through the menu, the pop-up menus are not showing. I guess the menus from the top are. Yeah, so the menus from the top are showing, but the context menus, which I get by clicking inside the panels here, are not showing.
Right. I think sharing the screen would fix that, but I don't know if that's possible for you the way you have your system, where you're presenting.
I can certainly try it, but it was kind of misbehaving before.
And maximize your whatever your Scholaska stuff is. Yeah.
Okay, now you're seeing it. So when I right-click in one of these panes, I get a pop-up menu that allows me to get to the documentation or to do various operations like sort the items here. So what I was doing in the middle panel here was going into the sort option here, and then sort by name or sort by inclusive or exclusive value, and then applying that sorting. Yeah, now you hopefully see it a little bit better. It's certainly a very awkward way to get a flat profile of the time in the different parts of the execution, but it's the way in which it currently is presented and fits into Cube here. I don't think I was using the other one. And there are different options that you can use for finding something of interest as well. Subroutines is not very interesting, but I was looking for MPI reduce before, so I could bring up the dialog and search for that. And then we're still in the flat list. It's probably more interesting to find it in the call tree. So if you're looking for something, that the find can be a useful way to look for things as opposed to expanding the entire tree. Expand all. And for some applications here, it's relatively manageable. For your larger, more complicated applications, that tree might be rather more tedious to search through and to scroll through. How are we doing? If you didn't run Square, then inside here it would be you have the Scout Cube report, where it just has all of those basic metrics that it has calculated or might calculate as a list. So if you know what you're looking for, you could use this. But we think that having things in the structured tree presentation is more convenient, and so we recommend that you use Square for doing that. Someone was asking about the Sunburst yesterday, which by default doesn't show you anything very much because you need to expand it to see what's happening at the different levels. And if you expand it to the lowest level, where you're looking at all of the threads or all of the processes, then that Sunburst gives you a graphical perspective of which threads are involved in that operation. In this case, it's an MPI send, so it's only on the master threads. You see the relative amount of time on each of them. If I go into the peer percent, and that also works better here, then it's coloring things with the maximum value in the high end of the scale, this red value, and then the other ones are fractions of it. So this one is a 50% value. This one I think is the highest value, 100%, and this one is probably close to 100, 90%. So by right-clicking here on this on the Sunburst, you can control it and you get additional dialogues. Likewise, in the topology, if I right-click on here, it brings up the information about what I'm looking at in the what I've selected, or I can select with the left mouse button, or I can use the right mouse button to show and see different values. So there's lots of things you can do with Cube, and I don't want to go through every little feature, but feel free to try things out yourself. And if you have questions about something that you find confusing, you're not finding so understandable, then let us know. Previously, we haven't really talked much about the, I want to go back to the trace analysis, which I had initially. Or let me go to the profile here. One of the tabs here was offering a high-level assessment based on whatever call path I select. So if I don't select a call path, it's for the whole application. If I just select the part that's the iterative solver here and get the calculation for that, it's telling me that within that part of the code, there's load balance and there's communication efficiencies which are less than perfect. This default assessment here is just looking at MPI, and that's probably not so appropriate for a hybrid application. So for a hybrid application, you would probably choose the hybrid assessment here, and then you get the different hybrid metrics calculated at the process level, telling us there that at the process level, the load balance is good, but it's within the threads that we have inefficiency in the Openmp parallel regions, which in this case is a load balance inefficiency. There's also a certain amount of the code which is AMDAL efficiency, which is outside of the parallel regions. Here it's showing as a relatively small proportion of the total. Some of the metrics are not shown because those come from the trace analysis. So that's why they would only appear if I was looking at what comes from the trace analysis. Again, in the general tab, calculate those values. Here, it's giving me a more detailed breakdown as to what is going on at the MPI level, but I need to switch to the hybrid assessment. And again, here, it's saying that transfer efficiency is relatively good, but not perfect. Serialization efficiency here is how things change from parallel region to parallel region. If that load balance is moving around, it's not in this case, it's fairly static, and that's why the serialization efficiency is being reported as being relatively high. But if any of these metrics need further explanation, I can click on them, and the dialog, which hopefully you see now, explains how that metric is derived and how it's related to the other metrics that are being shown. What is the runtime threshold at the top? It's something you can ignore. What I believe it is trying to do is identify which call paths are the most interesting ones for focusing on. So rather than looking at the entire execution, it hasn't been able to identify what is the where most of the time has been spent here, which we know is here in the iteration. Perhaps if I lower this threshold, it will at some point figure that out, or maybe not. All of this is pretty experimental. I think that the runtime threshold at the moment is useless and can be ignored. if I don't want things to be calculating these metrics is fairly expensive, especially for larger measurements, larger profiles. So that's why often that's why it's not updated automatically. If it's automatically, then every time I select something, it will update. But since that can be expensive, it's usually best just to recalculate things when you're interested in having a new assessment generated. So once you've identified which part is the most relevant part to get this assessment curated for, then select it and then have the recalculation done for it. I'm guessing there's, I think I told people yesterday that there should be some additional help information that is provided by clicking on something, but yeah, it doesn't provide any help for this runtime threshold, so best to ignore it. Stop sharing this and wonder if I still have anything relevant on the slides to present. Find my collaborate window again and just share the slides now. We already saw the trace generation, the automatic trace analysis, the post-processing of the trace analysis, and the additional metrics that appear in the trace analysis, which, at least in the trace analysis, the online descriptions seem to be working. For the profiles, that didn't seem to be the case. Identify where the critical path time is spent, which in this case is not so interesting, but the things on the critical path are the parts that you might want to try and improve their execution time for. And yeah, we have a case study that is on the slides that we might look at in a minute, but I prefer to hand over to Christian to present, and we'll maybe come back to this and other case studies if there's time at the end. So Christian, are you ready to continue and present more about what you can get out of ScoreP?
Yes, of course. Let's start sharing. So yeah, okay. So this will just be a brief overview of some additional features provided by ScoreP. So there's not much relation between the features, so I will just go through them by one. Oops, sorry, this is page. Okay, so already mentioned yesterday, so there is a way to record memory allocation and deallocations using ScoreP. So this is limited to memory allocations and deallocations in your binary. So we don't see anything that is coming from shared libraries yet. So this will change in future. So we are able to intercept malloc, realloc, free, new, delete, and also memory allocations coming from MPI. So and we can use this information to determine the maximum heap allocation per process. We can also find some frequent small allocation and deallocation patterns, which usually should be avoided. And we can also find memory leaks. Well, we can find the allocation or the location where memory allocations took place and where is no corresponding deallocation. So again, if the allocation takes place in your application and the deallocation in some shared library, then you will get some false positives there, and also the other way around. Okay, so this is just interesting for the profiling at the moment. So there's no special handling in Scholaska yet. And I think, yeah, it's even not possible to analyze traces with this memory recording option switched on. So you can just use the usual instrumented binary. So the instrumentation for memory recording is already built in, but you have to activate it with this environment variable here for the usual malloc and free. And for MPI, there's a different variable. And for shmem, I think is also supported. There's it's then called scorpy shmem memory recording. So if you are using, yeah, this only works for heap memory allocations and deallocations. So if you have some static large arrays, then you won't see anything here. And also for Fortran, this at the moment just works for the GNU compilers. And here is it how it looks like in Cube then. So there will be an additional metric here, maximum heap memory allocated. And then you can see here on the right pane that rank 0 here allocated a little bit more memory than the other ranks. Also interesting is the bytes leaked here. So we see here 2 memory allocations, and we see the call path here. So it's in the function human readable, where we allocate 3072 bytes, and there is no corresponding free for this allocation. So this might be quite helpful in finding some memory leaks. So next feature is the performance counters. So these were briefly mentioned and we also saw the environment variables in the job script. So there are different ways or different providers of hardware counter metrics. So one is PAPI. This is a library that we usually use, but we can also access Linux perf counters, and I think there's also some R usage counters. And see, it depends a little bit on the installation you have. So what is available and what not, and you can find out by scorpy info, the command we saw yesterday, and then the config variables, and then just grab for metric, and you will see what your installation provides. So here, for example, we have the PAPI metrics. There are 3 variables, and then we have R usage, and we have perf, and then there's also the possibility to write in your own plugin. Usually the metric variables come in 3 3 variables per metric provider. So here this means separator. Usually it's just a comma, so you don't need to change anything here. And then you have this metric PAPI, which will, if set, will record the hardware counter at every region enter and exit for every thread. In contrast, we have this per process metric, which will record the metric only on the master thread. So, for example, if you have a shared at3 cache, for example, then you would just want to record this on the master thread. Yeah, you can find out about the counters that are available using either PAPI avail or PAPI native avail, or in the perf case, you can use this perf list and then specify the names provided by these tools here in the in the environment variables. So if you want to write your own plugin, for example, then just go to this GitHub page here and see some examples. Okay, next topic is the user instrumentation. So this is switched on with the -- user flag. So during instrumentation. And so the idea is to have some coarse-grained phases. For example, initialization, solver 1, solver 2, and finalization. But you can also subdivide very long functions. So for example, if you have a 800 line function and you want to know a little bit more about the details, what is going on there, you can put some macros inside the function to subdivide the function. This is available for C, C++, Fortran. And here, for example, we have a Fortran case. So we have a Fortran subroutine foo. And what we do here in Fortran and also in the C case, we first define a region and give it a name. So this will then be converted into a variable. So this Scorpy user region things here, these are some macros, so that get pre-processed. And once you have defined such a region, you can use it in the begin and in the end calls. So you have a variable and you can use it several times in this begin and end calls. You can also give it a type. So there are several types available. You can use a function type or a loop type. I won't go into detail here. So it's very similar for C or C++, can be both used for both languages. Here you have this define as before, and you have the begin and the end. For C++, it is easier. So if you put or if you create a block here and put the Scorpy user region at the beginning of the block, so this will then create a variable on the stack called the begin call, and here at the end the destructor is called for this special variable, and the destructor will then do the end call. So it's a little bit more convenient, but you need to provide this extra block here, which sometimes is a little bit tricky if you have variables that are should be available after the block and are defined inside the block. Okay, so then there's the option to switch off and switch on the measurement. So for example, if you want to ignore, let's say the initialization phase, you're not interested in it, then you can use the macro Scorpy recording off. You need to make sure that this is called in a serial context. Then do something that you are not interested in, and afterwards you can use Scorpio recording on, also in a serial context, to resume the measurement. So, and this is the same for Fortran and CC++. And here again, we need this -- user flag, and I forgot to mention before, to use these macros, we need to include for Fortran this Scorpy user.inc, and for CC++ this Scorpy user.h. Okay, next one. So yeah, we don't have GPUs on the ARCHER2 system, but there are lots of systems around that have GPUs, and so Scorpy needs to be configured to use some means to get information about GPUs. So there's, for example, the CUPT interface provided by CUDA. Then we are working on the HIP interface for AMD GPUs. So this is work in progress. We can query the OpenACC interface and also intercept OpenCL calls. So and to measure something when we execute the instrumented executable, we again need to specify an environment variable. So for CUDA, it's basically the Scorpy CUDA enable. So and there are several options you can specify. So and this can be seen in the documentation. So you can't see it here because this installation has no CUDA, but so to get the entire information with every possible options, you use this Scorpy info config var -- full, and then if you have CUDA in the installation, you would see options to that can be provided to this Scorpy enable CUDA call. So same is true then for OpenCL and for OpenACC. Yeah, here it's already mentioned. So the Scorpy info config var -- full gives you the whole range of options that are possible. Okay, and if you do a measurement and you look at the measurement using the Vampire timeline visualization, then you would see something like this here. So you have the master thread here, this timeline. Then you have a CUDA device here. You see some device activities. You see some host to memory and memory to host transfers, which are these black lines here. Here you see, I think this is a kind of call tree. So main calls reduce and OpenACC kernel. That then calls this OpenACC directive. And so the purple ones here are OpenACC calls, and the blue ones are CUDA API calls. So you see here that the OpenACC runtime internally calls some CUDA functions. So Next topic is C++ applications. So for C++ applications, we oftentimes have a quite high overhead. So especially if you use functions from the STL or Boost. So usually these functions are quite small. They are inlined, but yeah, and small functions that are instrumented create high relative overhead. So we saw this already yesterday. And for C++, it's even worse than for the Fortran code we had. So if there is a problem, depends on the compiler. So if the compiler instruments inline functions, then usually the overhead is quite high. So we know that the at least the older Intel compilers instrumented inline functions. The newer ones that are based on Clang don't do this, or they have an option to switch this off, which we use by default. So this problem is fading away a little bit. So, but with the Intel compilers from last year, I would say the problem is still there. So, and if this is really an issue, and you could either do some coarse-grained user instrumentation and switch off the compiler instrumentation entirely, or you can use sampling instead of instrumentation. So with sampling that we use in SCORP, you basically switch off the compiler instrumentation, but you still have the Openmp measurements, the MPI measurements. So and this will allow you still to do the weight state analysis, but everything outside MPI and Openmp, there you just get samples. And this, I would say, is still a little bit experimental. Sometimes we see some interesting stuff when it's used together with Openmp. So this also needs a special library to be available on the system. So on the ARCHER2 system, this library is not available. So this feature is not active by default. And with the newer compilers, I think there's less of a necessity to use this feature. And so it can reduce the overhead quite a lot. So here, for example, you see again a Vampire screenshot, and in the upper part we have measurement using instrumentation. And it takes significantly longer time than the measurement using here in the lower part using sampling. Then this is more for maybe the administrators of the systems, so we can wrap the interface of third-party libraries. So for example, if on your system users use some libraries very frequently and they are interested in the performance impact that using this library has for their own code, we could do two things. So we could instrument the entire library, so which is usually quite some work, or we could just instrument the calls to the API, but nothing underneath. So this is, if you are just a user of the library, usually what you want to see. This works for C and C++ libraries. This needs some help from Clang. So what we do is we parse the header files of the library and create some wrappers for the API functions. So yeah, this generating of the wrapper needs to be done only once. So it's a multi-step process. And then you install the wrapper, and then it can be used by the users of Scorpy quite often without any additional work. So there's an additional libwrap option that you need to give to Scorpy at instrumentation time, but otherwise it's no work, no extra work for the user. So it's just extra work for the one who installs the wrapper. I think, yeah, here is how you do this a little bit more explained. So, okay, so this is, I think, for the FFTW library. So you would use the Scorpy libwrap init command line tool. You give it a prefix where the library should be installed, and some options. I think this is language C. Honestly, I don't know about the CPP flags here, but yeah, and this creates a wrapper. Then you do a make check, and install check. And if everything works as expected, then this wrapper is ready to use for users of Scorpy. And this is how it looks like. Again, again a Vampire output. So you have here this purple one. This is the FFTW, and you see that is FFTW API calls are used just on the master thread of the different ranks here. Maybe it's also called here, but the colors are a little bit difficult to read. Okay, that's it for the additional features. Yeah, so the further information I think we showed already yesterday. So Scorpy is maintained by colleagues from Technical University in Dresden, RWTH in Aachen, and my colleagues in Jülich. So we usually have 1 or 2 releases here. So depending on when the feature gets ready. Next feature to expect is the support for OMPT. So this is the Openmp tools interface, which would then replace the Opari2 source-to-source instrumentation for Openmp, which source-to-source is usually a little bit tricky, especially when it comes to Fortran. Not all compilers support this OMPT yet, so this will be a transition. I think that will take a few more years. So until every system supports this OMPT fully. We also, this is more internal, but might also be recognizable by the user. So we try to have this link time instrumentation done in a slightly different way. So for some of these instrumentations, we just wrap calls that are inside the binary, but not inside of shared libraries. So we are going to change this so that we also see, for example, the memory allocations in in shared libraries. So yeah, but this is more internal stuff. Yeah, so if you have questions installing or using Scorpy, just send us an email. If you want to host a workshop at your site, then yeah, please let us know. If you need a special feature or please let us know. We are happy to receive some feedback. And that's it from my side. So we are a little bit early for the break. So Brian, do you want to present a case study or two?
Yes, let's do that.
Okay, then I stop sharing.
Of course, if there's any questions, it's good to have them at this point before we move on.
So I saw Mark's comment about the update on ARCHER2. Do we have any hardware counts available on ARCHER2 at the moment, or is sorry, I missed that bit, or is it just restricted?
There's certainly a
So you
subset
have,
available, yeah.
so there are hardware counters accessible via perf. I'm not sure if you have a global PAPI installation. Maybe I installed it on my own, but so if
The measurement I did included at least the instructions and cycles. I didn't look beyond that, but the basic PAPI counters were there.
So maybe we need to reinstall PAPI after the kernel change.
Yeah, I don't know. Okay, there does need to be counted. Yeah, okay. I just thought that's really like what Mark said. Sorry, Mark. Sorry, I misread Mark. Mark, up to you guys.
It might depend on which counters you're meaning. If they're not CPU counters, but are coming from, for example, the network. I don't remember what the network is that you have. Is it Slingshot or something? Those would not be coming from PAPI. They'd be coming directly from the external hardware or the external system software.
I'm sorry, I don't know any more details.
No, it's just a general point that there's processor-specific part, there's off-core parts, and then there's also network counters and file system counters.
Yeah.
And when you talk about kernel sections, it could apply to any of those.
I thought in the absence of the kernel modification, you could almost get no hardware counters at all. So it's good that you can get some. I've not been keeping track of it, but I thought the situation's okay and we'll get better. I thought the situation was a bit dire, but obviously not.
It's what's available is pretty basic and maybe not what you want in general.
Okay.
Sorry, may I also ask a question?
Yeah, of course. Go ahead.
Maybe I don't just understand the difference between profiling and tracing, but we get the information about profiling in profiling.cubex, right?
Yes.
And then we can get more information with scan -s option, right?
Scan
so maybe
-s
we
is the
go
same as profiling. Scan -s was the profiling, but we just did some processing to present more metrics from the basic timing metrics that were included in the profile.
So
and
maybe we yeah, Elena, go ahead.
And the results are then stored in summary.cubex, right?
Correct.
And then we can also trace our application with -t option, with scan -t, right?
Yes.
And the results are stats.
So the results are in this traces subdirectory. So if you do a trace measurement, this is a multi-step process. So first you run the application. This creates then the traces.otf2 file and the traces subdirectory. This is still the measurement part. And as we haven't switched off the profiling, it will also create an additional profile.cubex. Then in the second part, we use Scholaska to work on the traces in the traces subdirectory. There, the automatic trace analysis takes part, and the result of the trace analysis is this cube file scout.cubex.
Mm-hmm.
So the trace analysis works on the traces and creates a profile. And then you do this post-processing with this cube or with square again. And then from the scout.cubex, we create a trace.cubex, which has additional has this additional hierarchy. So this structured tree on the right side of the cube display.
On the
So
left side of the display.
Yeah, the left side, sorry.
And what was this summary .cubex again? That just contains more information than profile?
Yeah, so the measurement, the first measurement we did, or the measurement we did yesterday, created this profile.cubex. This is the raw measurement data. And you can reorganize this measurement data by using the square command. And then this creates the summary.cubex file. So it's the same, basically, yeah, it's an enhanced information, because during measurement we know about the region type, if the region comes from MPI or if it comes from Openmp. And with this post-processing, we reorganize the raw data into this summary.cubex. And the same is then true. The same is then true when we have this scout.cubex and we create the trace.cubex.
So we just get more and more data each time. Well, the summary contains more data than profile, and trace contains more data than summary.
Yes.
Yeah. Mm-hmm.
And what was the purpose of this -s option? That is just to get more information, more than that is just like between profile and tracing, right? Something in between.
The .s option that we used for the scan command is the default. So just by using scan on its own would be doing a summary profile measurement.
Was it scan.s or square.s? I think it was, Elena, you are talking about square.s or not? Oh, yeah, maybe.
That might be. Yeah, that might be. That might be that I'm confused. Yeah.
Yeah.
So the square.s.
Square.s is different from scan.s. Yes.
Yeah. So and square.s is basically the same as the score-p score we used yesterday, but the square.s writes the result of the scoring into a file.
Okay.
And yeah.
Okay. And for scan -s, that just gets with this we can get more information than when we only profile our application. Is that correct?
So not really. The scan-s is the same as doing a default profile. It's doing some additional checks to make sure that the executable is instrumented and to define a measurement directory, so to give an experiment title. But it's not producing more information than just running the uninstrumented executable on its own.
Okay.
You can configure things by adding, by setting some additional environment variables to score P, which the scan command will interpret as well. Or there's some switches, this -t switch to the scan command is the same as setting the equivalent score P environment variable.
Yeah, yeah.
Specifying a -f flag with a filter file is the same as specifying a score-p filtering file through an environment variable. So it's just a slightly different way of achieving the same thing, which may or may not be convenient or beneficial in some cases.
So the background that we have two ways of doing things here is that Score-P does not only provide some or create data for Scholaska, but also for other tools like Vampire, for example. And there usually you just run your instrumented applications and provide all the environment variables. So you don't need to have Scholaska installed to do a trace experiment. And then you need to provide all the environment variables yourself. When you have Scholaska installed, Scholaska provides some convenience commands that set lots of variables for you.
Okay, thank you.
So kind of to expand on her question, I think it would be really good if when you present examples, when you just show the profiling and then show that, okay, so here we're interested in something or here is the problem, but we do not see this information. So that's why we need a trace. Because when you say that, oh, the trace gives more information, it kind of becomes a bit too abstract. Like we don't really know why we need this information. So maybe if you could just open an example and say, okay, so here we see that profiling gives us this, but that's not enough. So this is why we want trace. Do you understand what I mean?
I think I understand. The profile, for example, tells you how much time is in different MPI functions. You saw that. The time in the MPI barrier, the time in the MPI all reduced to MPI send. Yes?
Yes.
But the assumption is that your application needs a barrier or it needs an all reduced, it needs a send. So the fact that, and whatever it does, it needs some time for that. But how much of the time in the send or the all reduce is waiting time is something that you can't tell from the perspective of the single process. So that's where the trace collection and the trace analysis is able to compare the timestamps of the events on the different processes and figure out where waiting was required. How much of the time in the MPI was required time to be waiting until the corresponding partner or partners in the MPI operation were providing the data that the recipient required.
Okay.
So and so there's a trade-off between which, yeah, if we use a very portable, easy benchmark application that can be built on every system, but this doesn't provide so much insight, or if we use a real-world simulation of, for example, sea ice, but that is not able to run on any systems without much work to set everything up. So there are examples, for example, that where the root cause analysis available in the Scalaska trace analysis revealed very interesting things, but this I think is not possible to do in a 2-day workshop. So maybe we should, yeah, provide some more motivation for the trace analysis, maybe just by providing some some case studies. So Brian, I think you have some more case studies there. Maybe this would be a good time to switch to these ones.
Yes, that's what I was about to do. But we were looking at the hardware counters, and what I see is that there's, I don't know, is that 16 or more than a dozen PAPI metrics which are defined. So those, they're necessarily hardware counters for branch instructions and for cache hits and whatever from some levels of cache are at least available. And of course, there's additional metrics which are not these derived presets, but are the native events. And for that, I expect there to be quite a lot more. As Christian said, there's various perf things that are coming from the counter, the kernel, but then there's also things that are coming from the hardware itself, such as SSE, AVX, flops, and then lots of obscure things as well. Required taking branch instructions, mispredicted. How many are there in total? 139. And for each of those 139, there's also qualifiers where you can, instead of getting all of the Dcache refills from system, you can qualify it with various subset counters. So there's certainly more than a few counters already available. Whether those are particularly useful ones, I wouldn't want to judge because I don't know what they mean in most cases, but that's also not unusual with hardware counters. And the ones which are considered most useful have been, oops, it disappeared or died, have been replaced by presets or been defined as presets. I think I lost my terminal. Yeah, that wasn't a good idea. Oh well. Oh, it disappeared a bit back. Yeah, puppy avail. So that's not the complete set. There's a lot of them are not defined for the current hardware, but some of them may not be relevant. So I'm not sure if level 3 caches are relevant for the AMD hardware that you have. So it's often the case that not all of the counters are relevant for every piece of hardware, for every processor. Yeah, and I'm not sure if there's additional components available, which would be for network, etc. Looks like they're not available, so those are all disabled at the moment, and those are things that would require kernel permissions to get access to the power management and energy counters, for if that's something that you're interested in. But that's always a moving target. For every new piece of hardware, there are different counters, new counters, and figuring out which are the useful counters and making them available takes some time. Examples. We have a few examples that are provided that you can look at, and I'll quickly look at one or the other of them in the time that we have available here. Where am I going? Shared. There's an interesting tool called Vampire here, but it's nothing to do with the Vampire trace visualizer, so it's very helpful. Samples. Okay, so some of these examples are just from the BT example that was built and run on Archer itself. I think these were mostly done when we did the course last year. So those are no more interesting than, well, they're more interesting than the, there are actually, it's the same class size, so it's no more interesting than what you've been running as an example. Let me take a look at this one. This is a little bit larger, so let's see how it looks. Okay. So this was a measurement that was done on the SuperMOOC NG system, which is one of the bigger systems in Germany. And this was done with, I don't know, 13,000 processes. So we see that there's, I think, 288 nodes here, each with 48 processors. So it's again, or it's 64 core, 48 core Skylake processors. So we have 48 MPI ranks running on each of the compute nodes of this system. And then there's, as I said, 13,000 of them in total. In the middle pane, we're looking at the total execution time. I adjusted the measurement here again, as we did in the BT example, because there's a large initialization phase where it's reading in and distributing work, which is a significant and interesting bottleneck in its own right, but it wasn't what the developers were particularly interested in. So they encouraged us just to look at the run simulation part, which is where the simulation is done. So this is doing a blood flow simulation through the human vascular system. Actually, no, this one is just looking at the brain itself, so the blood flowing inside the brain. So there are different geometries can be used, they're very complex geometries with lots of very fine connections between them, very irregular geometry. And so it's an interesting, complicated simulation, and it's also interesting to get it performing. Most of the time in the simulation is within this do time step. They have various parts of the computation being done, and then it's non-blocking point-to-point communication for boundary exchanges between the different blocks of cells of the simulation. So non-blocking send and receive operations to initiate the communication, and then waiting for all of the data coming in from all of the partner locations that are communicating with this grid cell. So what can we see from this? If we look at the proportion of time in computation, we see that a lot of it is actually in a not very interesting part, which is during the initialization, where we haven't we've disabled the measurement because we didn't want to collect lots of data from it. For the MPI time, we're seeing that there's a fair amount of time which is waiting time. So this is about 14% of the time is waiting time for the neighborhood communication. So that's a fairly substantial amount, and we could actually see that it was growing with scale. But when we're dealing with so many processes, it's quite a challenge to work through this list and figure out, are they balanced? Well, no, they're not balanced. There's various amounts of time here, but getting a perspective on what the range of times are is not so easy. And expanding this list so that we can see all of them doesn't really help, because scrolling through a list of 13,000 is also something that doesn't really highlight the ones that are taking the most time. So this is where some of the other presentations are more useful. This statistics presentation is showing from highest to lowest. Some of them have, at least one of them has a very low value. Some of them have much higher values. This box plot is showing the range of values from highest to lowest, and showing the percentiles here, 25 and 75 percentiles, as well as the mean and the median which are shown in the middle of it. So it's quite clustered here, but there's a few that are taking longer waiting time, and one which is spending very little, or at least one which is very little. If I go to the box, the Violin Plot presentation, it's the same statistics, but just a different presentation of them. And again, it's showing this very sharp line to the bottom is suggesting there's only one or very few that have very low waiting times. And then everything else, this shape here, which isn't very violin shape, but is a bit more regular, is showing that there's a distribution of waiting times from around 1,000 seconds for the slower ones down to 550 here. So there's certainly some amount of load imbalance that seems to be, that could be considered to be deriving this, but there's at least one process here which has a much higher waiting time than, sorry, a much lower waiting time than all of the others. And that's an indication that if you have one process waiting while, so if you have lots of processes waiting a long time while one is waiting for a very short amount of time, there has to be some sort of load balance that that is causing that. In the topological presentation, we capture, Scholastic captures the information about the MPI Cartesians that this application is using. So if you use an MPI Cartesian topology, in this case, it was 24 by 24 by 24 in the 3 dimensions. We capture that and Scholastic can present it. The topological presentation is showing all of the values as absolute values, but if I go to the peer percent, again, I can see the reddest ones are the ones with the highest values. Ones which are at the low end of the scale have the blue and green colors. And luckily enough, this one down at the bottom here has immediately stood out. There's one process there on the edge which had much lower values than the others. There's some other ones in other parts of this fairly large collection of processes that have lower values as well, but this one down here is really an outlier or very different from the others. And because it has a very low waiting time, that's probably because of the computation. If I look at the computation time for the code in the same section here, so this handle actors, it's highlighted in the opposite sense. So here it's shown as red. This red process down here is the one that has much higher time in computation than all of the others. And because it spends longer waiting for doing its computation, that means that when it comes to these neighborhood exchanges with its neighbors and then the neighbors of those neighbors, then they end up waiting as well. So we have a lot of processes waiting as a result of that single anomalous process. Are there more processes in here? Well, again, it's a little bit hard to tell even from this more graphical presentation. So the presentation that that I have found most useful is where processes and threads are shown. Now I'm looking at the 13,000 processes as one long list. Well, that maybe wasn't so helpful either. I still find it hard to figure out where the red one is, even if I can more conveniently scan through this big long list. But I also have an option here to split things, and the obvious way of splitting the processes in this case is by the MPI ranks, the MPI ranks per node. So if I use 48, then I have split things so that the 48 ranks which are on a single node are one of the vertical columns, and then across the x-axis here, I then have the 288 compute nodes in this case. And here is my red process, again, one of the ones that is on the edge that's different from the others. So that's the highest value there, close to 1,500 seconds. All of the ones that are near it are in the 800, 900 range. So that one is clearly anomalous, and by scanning through this list, it's really on its own. From this presentation, you might also be able to see that this first set of processes on the first nodes, first 10 nodes or something here, have a slightly more yellow color than the orange, and likewise the ones at the other end. So again, this is the nature of the decomposition and the assignment of the geometry, the geometrical computation to nodes, those which actually correspond to the top and the bottom edges have a little bit less work than the ones which are in the interior. So that's why they take a little bit of less time. And when we look at the MPI time for those, they show up again as a little bit redder. So here we have again a load balance. It's a load balance which comes from the decomposition in this case. And we have, in addition to that, one process that is very anomalous, that's very different from the others. Trying to figure out why it's anomalous can take a little bit of work. One, there are different hypotheses that you could investigate. You could see how often it's doing the calculations. Is there any difference in the amount of messages that it's sending and receiving? Where's the visits count? I'm looking at visits. It's doing exactly the same number of wait all operations as all the others. So that doesn't explain why it's turned out to be faster. In terms of the data that's sent and received, there is a variation because it's a complex geometry. If you are knowledgeable about the human brain and how this data set is distributed, maybe you can discern a pattern in the different colors here. But basically, it's a very irregular geometry, and therefore it's an irregular pattern of sends and receives. The numbers of sends and receives and the corresponding bytes that are sent and received also is varying. So there's lots of reasons why there might be load imbalance and why one process might have very different communication characteristics from the others. But none of it is explaining why it is so different, because there are differences, but they affect lots of processes here, not just one. And therefore, going back to the computation, which is really the cause of the problem here, it's not the fact that the communication is irregular and complex. It's really something from the computation itself that is causing this this anomalous behavior. That motivated, in this case, looking at different hardware counters to see if those would provide some insight. If we look at the number of instructions which are being executed, that's a measure of the instruction intensity. Again, there's a variation. There's some more orange, or some nodes which are more orange than the others, but there's not really that big a difference. And the one which is still highlighted here as being different is not so different from all of the others. And back in the statistics, yeah, there's some difference here, but it's not so huge. But if I look at, for example, the resource stalls, or refining resource stalls to be more specific about memory stalls, that's where this node, this core, in fact, is standing out as being very different from the others. So for some reason, that core has suffered from many more memory stall cycles than any of the other threads, any of the other cores in this simulation. In the topological view, I could spot it. In the system tree, it stands out. In the statistics, it stands out. Identifying it in the basic tree itself is not so straightforward, but there are ways to facilitate figuring out where these different values are. Just applying a sort here, sort by value, doesn't really help because I have things structured in terms of compute nodes. So I really need to get rid of the compute nodes and get rid of the switches because it may have been running on different switches. So we'll just get rid of that unnecessary part of the hierarchy so that I have all of the processes here, all of the MPI ranks at the same level. And now when I do the sort, I should be able to why is it not sorting? Okay, now it's sorted. I see one value for one process here, 8,639 of the 13,000 processes in total, is taking 40% more time, has 40% more stalls than any of the others. All of the others are in this range of 62 to, I don't know, 40%. Well, some of them have very few stalls, but there was one there at the top that had a very large amount of stalls, much larger than any other rank, which is not something that is easy to explain. And that's the one that we were highlighting in our topological presentation here, which was one way of helping to identify it as opposed to working through. Let me look at the computation time. So here it's computation time for our extra process in the ranking here. It's the one that is taking a third or more time than any of the others. All of the others are in this more moderate range from 35 to 65%. So there's definitely a load balance, but a load imbalance issue. But here we have one rank that is standing out with a very different amount of time from all of the others. It turns out in this case, this is an artifact of the way in which the hardware memory is mapped into level 3 caches, or the caches of the processor in the Skylake processor. There's a complicated proprietary algorithm, and in various cases where there's a lot of memory being accessed, that mapping algorithm is not very efficient, or it ends up with very inefficient handling. It's going to vary from run to run. It varies from, and in run to run, it varies from core to core. So where I've done multiple measurements, one after the other, using exactly the same processors, it was different cores that had this anomaly, and sometimes it was 2, sometimes it was 1, sometimes it was 3. So there was about a 1 in several thousand chance of having a very bad mapping of application memory into the caches, and then suffering from stall cycles when this application works through the data set to access those access that memory and process it. Okay. So so that was one example from a real application running on a real system, showing a real problem that by doing, in this case, hardware counter measurements of the appropriate type. And yes, it took some trial and error to figure out which hardware counters showed this issue and which ones were not related to it. But it was one way to be able to get a different perspective on this performance problem. There are other cases that are that were documented in this case study where all of the cores on a particular node had a problem with accessing memory, and that could be tracked down to defective memory modules in that node. And then all of the accesses to memory from that node, or one of the sockets in this case of that node, had much degraded performance and performance issues. That sort of problem is easy to work around. You just ignore, exclude that process, exclude that node from subsequent measurements. But in this case, where you have a problem that's changing from run to run, that changes from core to core within a run, you don't have the ability to easily work around it. You need a more dynamic approach to address this load balancing issue. Yeah, I think that's one example that's taken us up to lunchtime. You can look through some of these other examples if you're interested. The tea leaf one is also documented on the slides that we didn't present, but is available for you to look at. So I think at this point it's good to take a break for lunch, and then we would come back and again work with your own application codes and see what sort of issues we see with them when we do some measurements on Archer. But we do that in an hour's time, or do you need a bit longer than an hour?
Yeah, 1:30 I think is a good time. I'll put up a...
1 hour's time. Okay.
I'll